So every morning this week we're going to have two talks by one person, which are kind of introductory in nature, and the first one today by friend and past colleague Markus Linckelmann. We're going to talk about the intelligence theory, unit systems, and homology.
Thank you very much, Ron, for the introduction, and of course, thank you to all the organizers for organizing and inviting me in the process to this workshop. So the title looks a little bit like the theory of everything. So and so does the now how do I move on from here? So the arrow, the down arrow does not respond. Right arrow does also not respond. Yeah.
That's not good.
Okay. Oh, yes. How did you do that? Okay, left and right. Yes. Yeah. Yes, we can. Okay, right. So left goes forward. Okay, so let's try again. The first slide, if it comes, yes, is a little bit how things I'm interested in fit into a picture that includes groups, categories, then a bit of homotopy theory, logical spaces, and whatever is associated to those things. From groups you go to algebras, from spaces to the cohomology, and commutative algebra comes into the picture through some properties of X algebras. They may be finitely generated, and if they are, then you can actually apply some commutative algebra methods to those. So this is just to give you a very rough overview of various things. And because there are so many different aspects to this, I will necessarily have to be a bit superficial in places. But I'm going to start with a very general introduction to the left side of this picture. I want to talk about the left lower corner, namely groups, as some categories that we associate with those. And those categories started out as what group theorists would consider to be the p-local structure of finite groups. Now, when finite groups were investigated in an abstract fashion, then one of the ways of going about this is, like in many other areas of mathematics, you pick a prime p, try to look at things from a p-local point of view. And in group theory, this means, well, you choose a pseudo p subgroup, but that's of course not enough to determine the structure of the group G. So what you then do is you want to track information of the way in which G acts on a pseudo p subgroup by conjugation. And this is encoded in a definition that we now know called the fusion system of a finite group G on one of its pseudo p subgroups P. And it's just a fancy way of encoding conjugation on the elements of P. So what we do is we describe this in terms of a category where the objects are simply the subgroups of the pseudo P subgroups. And the morphisms are various group homomorphisms that are induced by conjugation with elements in G. And I want to be really pedantic and write this out in a completely explicit way. So for any two subgroups Q and R of P, the set of morphisms in this category F sub P of G, and sometimes it is convenient to just put a subscript of G. So that's a definition of this equality there. Consists of all and necessarily injective group homomorphisms phi from Q to R, for which there exists a group element which realizes that group homomorphisms through conjugation, and choosing the interpretation of putting the X on the upper left of the U for interpretation X inverse. And whenever you define a category, well, you have to define objects, morphisms, and you also have to say how you compose morphisms. In this case, that's very simple. We just compose group homomorphisms the way we do. So that is a category which encodes what we nowadays call the p-local structure. Let me just very briefly mention a couple of very old classical results on fusion systems. That is also a pretext to introduce another term here, namely, it could happen that you have a subgroup H of your finite group G, where the fusion, that is the fusion system of H or P, is actually the same as that of G itself. That can happen because it might just be that every conjugation by an element in G could already be realized by conjugation is something in H. In that case, we say that H controls G fusion in P, and one of the old theorems on this topic is the theorem of Frobenius, which he didn't formulate that way. But nowadays, the way we would write this is by saying that the fusion system of the magnetic G on P is already just the same as the smallest possible fusion system that you can put inside the fusion system of the group P on itself. So that is, every conjugation in G is actually realizable by some conjugation with an element in P itself. But then G must be something that is actually just P, except for P prime jump that the fusion system can't recognize. So you have for G the structure of a P prime, normal P prime subgroup, that's O P prime G. That's the group theory annotation for the largest normal P prime subgroup. And then P acts on that. And this is the structure of the group G. Groups of this type are called P nilpolar. And then there's another theorem by Burnside, which I want to briefly mention, which is that we know fusion systems of finite groups when the CELO is abelian. They're very simple. Namely, the fusion system in that case is already controlled by whatever happens in the normalized of P and G. So any set G of P is the subgroup of all elements under which P is invariant. And it turns out that in that case, the fusion system is actually just simply the same as the fusion system of a semi-direct product P times E, where E is, well, it's the automorphism group in the fusion system of the group G. So it's the normalizer where you mod out by the centralizing. So that's a general thing when you look at automorphisms in a fusion system of a G, where they come from elements which normalize the group, but then you mod out the centralizer because that doesn't do anything on that group. So the theorem of Burnside is an easy 10-minute exercise if you know Euler's theorem. The theorem of Frobenius is not that for that one. So okay, so before I move on to talk about fusion systems of plots, which is what I want to do because one of the reasons for there to be an abstract theory of fusion system is that there's another source for categories that look like fusion systems of finite groups and have very similar properties, and that come from block theory. And before I describe those, they're hard to describe, I want to just make a connection between the fusion systems of groups on in terms of group item. So I'm going to pick my prime as before, and this time field characteristic P, no further assumption for now. And I have finite field and syllogism. Now, when you take any subgroup Q of P or T in fact, what I do is I'm going to look at bimodals where I take KG, which is a regular bimodal through left and right multiplication. And I can restrict on one side, on the right side in this case, the action from G down to Q. So that gives me a bimodal for KG on the left, KQ acting on the right. So as vector space is equal to KG, but the bimodal structure has been restricted down to KG and KQ on the right. There's something else I can do. If I have a group homomorphism between two subgroups Q and R of G, I can take my KG, first restrict on the right model structure down to R, and then transport this to a KQ model structure via the homomorphism phi. So if I take an element little u in Q, that's going to act on the right by multiplication with phi of u. That is now also a KQ G, KQ bimodal. Well, the KG actually on the left is unchanged, I've never touched that. And on the right side, well, I just go down in this two-step process, first down to R, and then pulling that back to Q via the cohomological bar. So I have two of these bimodals. And the proposition is that such a group homomorphism, well, between two subgroups of that cellular P circle which I picked, that such a group homomorphism belongs to the fusion system of POG. So it's induced by conjugation with an element in G, if and only if these two bimodals are isomorphic. And one direction, very easy to prove. I was tempted to put on those slides, but then I would have run out of time. This is only 2 slides it takes to prove this. One implication is immediate. This is an isomorphism in particular as left KG modules. So it comes from right multiplication with something. So if you have already something given, namely if you know that phi is induced by conjugation with an element X in G, you just take right multiplication by that element X and you get your isomorphism. So that's straightforward. The other direction is a tiny bit of work. You need to know a few things about P-permutation modules and things like that. But there's no difficulty. The point of I want to make here is that there is a close connection between the fusion system and the bimodal structure of KG as a modularized bimodal over itself. And then you just restrict it down to the various P subgroups that you are interested in. One thing I think I put on the slide but forgot to mention is that, of course, the choice of the serial P subgroup that I made is not creating any difficulties because all serial P subgroups are conjugates, so all fusion systems will be conjugates. So everything that I'm saying here is unique up to the obvious conjugating that if you change it from one pseudo to another. Okay, so this is just a taster for towards trying to get to the bit of block theory and trying to describe why it is or how it is that blocks of group algebras also give fusion consistence. And for that, of course, I do need to first mention a few block theory basics. What is a block group algebra? This time, for convenience, I'm going to pick my field to be algebraic and closed. That's really just for convenience, so that I don't have to worry about non-split algebras. But everything, or many of the things I'm going to say, remain true for arbitrary keys of prime characteristic. So the starting point is that you have a group algebra KG, and this group algebra may not be indecomposable. Actually, in general, it's not. It's quite a rare phenomenon for a group algebra to be indecomposable as an algebra, meaning you can't write it in a non-trivial way as a direct product of other algebras. So let's do that. Let's just write KG as a product of its indecomposable algebra factors, and those become the blocks of KG. So KG can be written as some B0 times B1, etc. times BR, where each of these factors BI is an indecomposable algebra. And then it's an easy exercise to see that what this means really is that your unit element of each of these algebra factors is going to be a primitive idempotent in the center. Primitive comes from the fact that you can't decompose this algebra any further. And central, the direct product decomposition tells you right away that the unit element of this, each factor has to be a central idempotent. And you can therefore then write each BI as the group algebra times that central idempotent, or times that unit element of your block. And writing it that way tells you one other thing. It tells you that this is also a decomposition as direct sum with bimodals for KG acting on the left and on the right. And each BI, of course, is a bimodal over itself, and it's annihilated by all other indecomposable factors. That's a biological KG. And obviously insisting on the difference between direct products and direct sums, because this is a direct sum in the category of bimodules. That's an additive category, so direct sums make sense. But algebras are not, in an obvious way at least, an additive category. So this is not a co-product in the category of algebras, it's a product in the category of algebras. You have canonical projections, but you don't have canonical projections, which are universal as algebra homomorphisms. Okay, so let me just drag down two extreme cases, P groups to P prime groups. If P is a finite P group, then nothing is happening. That is one of those cases where the group algebra is actually indecomposable, and in particular, KP is indecomposable as a biological itself. In fact, there's a bit more that we know, then KP is a local algebra. So the augmentation idea, which is the kernel of the canonical algebra involving from KP to place and group elements to on, that is a unique maximum ideal. So now that's the radical of the algebra. So if you divide KP by its radical, you just get a copy of K, which tells you regulate that this is an indecomposable algebra. There are other indecomposable group algebras which are not local, but that cannot go there. So this is one important special case. And then the other important special case, of course, is if the group algebra is not has order divisible, not divisible by P, then this is going to be a direct product of matrix algebras. And I wrote it down in such a way that there's one factor like equal to K. There is always one dimensional direct factor in such a group algebra. Here I do need to know that my field K is large enough. If it weren't algebraically closed, then you would get some division rings possible. So this is where I'm making use of this convenience of having my field algebraically closed. And in general, we will mix of things. In general, finite group algebra, these blocks, and some of them may be matrix algebras even. Most of them will not. Not, it just depends on the group in general. Okay, so now, as I said, we want to get to the point where we can define something that looks like a fuse that we attach to such a block algebra. And that's a notion that goes back to Brouwer in the 1940s. So it's the definition I'm going to present of a defect group is equivalent to Brouwer's, although he wrote it down in a very different way. And why do we need such a thing? Well, we need to start a finite P group associated to a block so that we can talk about something like fuses. So fuses is always something where the starting point is some finite P group. So let's see what we can do here. Let's just take for now a random P subgroup of G. It doesn't have to be pseudo P subgroup. Then trivially, if you collect the elements which are in P, and then the elements which are not in P, where you get a direct sum decomposition as vector spaces, where one of the vector spaces has the elements in P spaces, and the other has the elements that are not in P spaces. And then this is a decomposition as buckets for P on P, because if something is outside of P, you multiply it with something inside of P, but you stay outside of P. So this is a binomial. That tells you that KP is always an indecomposable direct sum of KG as a binomial for P on both sides. But as I said earlier, by last time, we also have a direct sum decomposition as a direct indecomposable KG models. And I can restrict, of course, this decomposition down to P times P. Then the blocks may no longer remain indecomposable if I restrict both sides to P. It doesn't matter. What matters is that we have a theorem which is called the encroachment theorem, which says that essentially decompositions of models in finite dimensional models into direct sums of integer persons are unique up to isomorphism at order of science. And that uniqueness tells us that therefore, this Kp, which I know to be a direct sum of Kg is Pp order, and I know it to be indecomposable, it must show up in one of those blocks Bi as Kp bimodel. And with that, I can just simply write down a definition. Take one of those blocks of Kp, so B is one of those modules. And for a defect group of B, I'm just going to pick a maximal P subgroup such I've seen many reactions to dividing people, but not this one. Here we go. So a defect group of block B. I just take a maximum piece of subject to the property that Kp as a binomial is isomorphic to a direct sum of B restricted to P on both sides. And insist on isomorphic because that copy of Kp need not be the copy that I written down at the top of the slide. It's only after isomorphism that the quotient theorem tells us that decompositions are unique. So it may be an isomorphic but different copy of Kp that shows up in that block B, and you just pick one that's maximal. So from a philosophical point of view, what have I done here? I've basically replaced similar piece of groups, or piece of groups in general. I replaced them by these binomials, Kp. They're indecomposable. My building blocks of these binomials. And then I look for the biggest P such that Kp shows up as an indecomposable direct sum in that block. So far, so good. This definition doesn't tell you a thing about whether it's useful or not. It's just something you can write down.
So this be linked in somewhere?
Well, exactly. So there are all these questions on my next slide. So, properties of defect groups. So first of all, they do behave a little bit like pseudo-defect groups. They are unique after conjugacy. So you get a conjugacy class of piece of groups and so attached to your block. So this is already the first key step that we have now achieved. We found a way of attaching a P group unique up to conjugacy with any block of the algebra G. And I do want to mention a slightly more complicated looking definition, possibly a alternative definition of defect groups because it carries more information. This one says that, in my definition that I took B, I restricted it to P on both sides. Now I go the other way around. I stop at Kp, I induce it up on both sides. So I tensor Kp with B and P on the left and right. And I look whether or not B itself shows up as a B bimodular sum. And if it does, great. Then I know that P at least contains a defect group. And if I take my minimal subject to this property, then that is also that gives me the defect group. So there's this dual way of going about defect groups. Either it's maximal P such that Kp is a summand, or minimal P such that B is a summand of B tensor Kp tensor B. And this definition tells you that any B module is a direct summand of some Kp module induced up to B. So the complexity of the representation theory of P algebras will have a major impact on the modular representation theory of blocks, simply because you know you can get to any module in your block by taking some module for Kp, inducing it up, and taking it possibly direct sum. This is why this definition actually tells you more about the nature of defect groups. There is one block which is nicer than all others. That's what we call the principal block. If you look at group algebra, it's actually Hopf algebra. So it has, in particular, an augmentation. That's the algebra homomorphism from KG to K, which just sends every group element to 1. And well, this kernel will contain all blocks except one. And that one that is not contained in that augmentation idea, that is called the principal block of KG. And it turns out so that the defect roots of the principal block are actually pseudo-decent. So the pseudo-decent roots always do show up as the defect roots of some block. And when your block has trivial defect roots, the trivial root 1 as necessarily unique defect root, that is precisely the case when your block algebra is a matrix algebra. And we call these the blocks of defect 0. So this is a bit of a funny terminology. They're blocks with defect group 1 that they call defect 0 blocks. But that's because Brower picked this terminology where the defect is actually p to the order to the d of the defect. So defect 0 blocks are matrix algebras. And I think there's no exaggeration to say that identifying the blocks of defect 0 in finite group algebras is one of the big challenges in block theory. So there are some conjectures, in block theory which revolve around this theme of getting to some numerical invariants such as number of characteristics in the models of group algebras. I'll mention a few later on. And I forgot who said this, but somebody once said defect 0 blocks are the black hole of representation theory. So they're really hard to get to and understand. So this is something. There's no reduction possible. They have already trivial defect groups, so you can't hope to get them through an inductive process. And so the conjecture I want to mention, because it's related to this, is Albert's weight conjecture. And I'm going to first mention it not in its most general version, but just for groups, and talk about the block theory version later on. So suppose we have a finite group G, and we denote by a little L of KG, well, the number of isomorphism classes of simple KG numbers. And that's a finite number because it's a finite dimensional algebra. We denote also by W of KG the number of defect 0 blocks of KG. And so, in other words, this W of KG, W for weight, is the number of direct algebra factors of KG, which are matrix algebras. And there's another way of saying this. The W of KG is just the number of isomorphism classes of simple projective models. So, when you have a block which is a matrix algebra, then actually the corresponding simple models that comes from that matrix algebra is a simple and projective model. And these are exactly the simple projective models. So this W of KG is always less or equal to the L of the G. Albert's weight conjecture for groups. So Albert stated this, I think, in writing in 1987. People have told me that the conjecture has been floating around for a few years before that. It just says that, roughly speaking, the L of KG, which is the number of isomorphism classes of simple models, is sort of something that looks like a p-local invariant. It's on the right side. I'm going to take the sum indexed by p subgroups Q up to conjugacy. I'm going to look at the group algebra of the normalized of Q divided out by Q, which I can because the normal Q is normal and it's normalized. And then I look at the number of defect 0 blocks in that quotient algebra group algebra. I pick them out, those out there. Sum them up, and miraculously I should be getting the number of simple models of the group algebra. So this is one of the grand mysteries in this business. And when you do calculations for specific, say, simple groups where you want to check whether this is true, then very often you realize that it's just a miracle that both sides give you the same answer. On the right side, you will note that there's one summand, which is not really P local, because for P equals 1, the right side is just W of kg. So if you bring that to the other side, the L of kg minus W of kg, that is really, in some ways, a P local invariant. So the W of kg that appears on the right side is for Q equals 1. So this is the nature of many conjectures in modular representation theory. They try to describe numerical invariance of a group algebra in terms of p-local information, to the extent that one can have to be able to do this. And there's a version which is much harder actually to write down for blocks of this, which I will write down in a particular way a little later on, where we have a bit more the cohomology to play with. And also, I should be saying, I'm really shortchanging other people. In many cases have been checked. So there's an awful lot of work has been done by lots of people, and I just didn't have the time to go through a list of those things. But so Puig himself, before he made his conjecture, he wanted to make sure that it's true symmetric groups and general linear groups in finite restaurants of Holland. So Puig did that already very early on, and Puig's philosophy at the time, he said once to me that was that, well, if something works for symmetric groups and for general linear groups, it should be true. So there's one other type of conjecture which I very briefly want to mention, although it's not strictly related to many other things I'm going to do. That is Donald's finite conjecture. So one way of looking at things is, well, you could ask yourself, here you have a block with a defect group. Can you write down numerical invariance of the block, like numbers in the lines? But another type of question is, if you fix your defect group after isomorphism, how many different possibilities are there for your block properties? And Donald's finite conjecture says that, well, in some sense, there are only finitely many possibilities. There should be only finitely many possibilities. And I have to say, of course, up to what? Just a quick reminder to algebras, A and A prime called Marite equivalent if they have equivalent modular categories. So modular categories are abelian categories. You've currently spoken on the rest. So this is an equivalence as abelian categories. It's sufficient to specify that's an equivalence as k-linear categories, because the abelian structure is a property of these categories, so that will follow. So either as k-linear categories, if you wish, or as then abelian categories. So this is what we say that so Marite equivalence. And now I keep my notation from earlier. P is prime, k is an algebraic plus field of prime characteristic P. And Donovan's conjecture, which was made around the 1970s by Peter Donovan, says that, well, if you fix your finite P, then up to Marite equivalence, there should be only finitely many blocks with that defect group. So you should be able to write down a finite list of algebras such that every block with P as a defect group is Marite equivalent to one of those atoms in the list. And actually, these are two very different problems. One is to show this finiteness. Another one is to actually write down the corresponding list of algebras. So this is one of the key conjectures. Is still open, but Donovan's conjecture as Puig's conjecture have been proved in loads of cases. I'm just going to mention a couple because some terminology I want to introduce. So early on, it was understood that when P is cyclic, then any block algebra has a simple combinatorial description in terms of what's called the Brown tree algebras. I'm not going to define and introduce them, but these are algebras which have a simple combinatorial description, and they are algebras of finite representation. So they have to be finitely many integer positive models, and more. They're very well understood. Then some years later, Erdmann wrote lots of papers on what we call blocks of tame representation type. I'm going to single out the case P equals 2 where P is applied 4 group. In that case, we know a bit more than just that there are finitely many variables. The block B is more equivalent to either the defect group algebra itself. That always happens, of course. Yeah, a block algebra is simply possible. It's only defect group. Or the alternating group A4, or the principal block of the alternating group A5. So that this is, I would needs some pretty sophisticated machinery to prove this. And just to give a little bit of a feeling for what has happened later, so people kept working on this. So there's this paper by Eaton, Kilson, Mazambano from 2014, where they look at all elementary two groups as potential defect groups, and they show that dominance conjecture holds, but in this generality, they can drag down these complete lists in low rank, yes, but not in general. And it should also be said that this now uses the classification of finite simple groups. So for some of the more advanced results in this business, one needs the classification of finite simple groups. Okay, right. A few resistors blocks motivation. Introducing a few resistors of blocks always reminds me of when you do your first real analysis course, and you have to introduce the definition of a limit in terms of epsilon and delta, and then you see these panic faces, and then you're having a hard time to get this across. So every time I talk about few resistors of blocks, I feel that way. And so every time I try something different, so let's see how it goes. I just wanted to briefly motivate what we're going to do in terms of the proposition I mentioned earlier, where I said that, well, in the finite group G, the fusion system can be detected in the bimodal structure by just looking at these bimodals KG restricted to Q in two different ways. First to Q and then first to R, and twisted is fine. And you might want to say, hey, that looks good. Why don't we do this? Let's replace the KG by B. It would be very tempting to just do the same thing, take a block, but then you can restrict it in two different ways. Once directly down to Q on the right side, once first to R, and then twisted with a morphism from Q to R. And you sure can write down a category like that. But it just doesn't work. It gives you a too big a category. And I mean, the way I've written it here on this slide, it just tracks too much information that comes from the group G, which is not relevant to the block from B. Then your block B might just be a matrix algebra, in which case your group G is sort of irrelevant for the block structure up to metric grids, because up to metric grids, that block is just a copy of K. So in that case, what you really would want to the fusion system to be of the defect zero block is the trivial fusion system of the trivial group 1. But if you use B, the one I indicated in the paragraph in the middle here, well, you would still get all these groups and all between these groups. So this is not the right way of going about it. There's the deeper reasons why this is completely not functioning that way, which is that if you do this, then you can't hope from this category to get to something that looks like a classifying space of a block. So definitely what we need to do is we need to first of all replace pseudo piece of proof by defect group. And the other thing is, this is where the trouble really starts, is we need to be careful about morphisms. So let's pick a block of KG. And if you pick a defect group, then let me remind you, this is just a piece of group such that P is maximal subject to the property of KP being isomorphic to direct sum of P as a binomial for KP. What that means is, well, as I said earlier, taking all of B and putting it into this earlier proposition on characterizing future system of finite groups is too big. So let's cut down this B a little bit. I'm going to restrict right away attention to the B times KP binary structure of B. And I pick amongst all integers with the sums I find in this restriction, a sum of x, which still has this property that Kp will show up as a direct sum. I can do this thanks to the Kroll-Schmidt theorem. Okay, so now I pick this integral with direct sum. It's not unique, but we'll come to that. So fix such a Kp binary x. So in a way, what I'm doing now is instead of requiring that something is a subgroup of something else, I'm requiring that integrable Kp binary is something of something else. And so here the fusion system, we can write it down on this slide. It's a complete definition. It's just with all this definition, you see for the first time it won't tell you that much. So the fusion system is the category where you take as objects the subgroups of your different. For the morphisms, you do exactly what we did in this translation from fusion systems of groups to their interpretation in terms of the binomial structure, except that we now consistently look at binomials which keep in the picture direct sum of the people under consideration. So I take as morphisms those two homomorphisms from Q to R, for which, first of all, you pick an intercomposable summand of U of X restricted to Q on the right side, but you make sure that your U, when you restrict also to Q on the left side, there is still a copy of KQ in the picture. You do the same thing for U. And then you need to make sure that when you restrict your V not to R, but to be assigned to Q, that it has a summand isomorphic to U. It's no longer the case that U is isomorphic to that restriction V sub R. That's because Q and R have different sizes. So one may be a summand of the other. So this is a complete definition of how to get to a fusion system of A block B. And that was really the reason for wanting a notion that in an abstract way describes a fusion system without any reference to groups or blocks. So I need to briefly mention those properties which require explanation. First of all, this summand X of B restricted to P with KP as a summand. It's not unique, but it's unique up to some optomorphism in the normalizer of P. So this is one important remark. So these fusion systems are, again, they really use unique only up to some combination of elements in the normalizer of P. The fusion system of block is always a fusion system, the category of the fusion system of the group G for any pseudo that contains P. But it's not necessarily a full subcategory. So this is a delicate aspect of fusion systems of blocks, that you do get subcategories of the fusion system of the group, but they need not be full subcategories. Now, the nice thing is that when you look at the fusion system of the principal block, then, as I said earlier, the defect groups are the pseudo-P groups, and well, miracle, we get actually the full fusion system of the group G that way. And actually, we do not even know at present when a fusion system of blocks yield new categories. So it could very well be that every block gives you a fusion system, but that's already a fusion system of some potentially other finite group. And many people have asked this question, so I'm writing this down as a conjecture, but I think this is one of those folklore conjectures which evolved over the last 30 years, which basically says that, well, if you have a block of a finite group algebra and P is your defect group and F sub P is your fusion system that is given from this by this block. Well, then there should exist some potentially other finite group H, which has nothing to do with that group G, but has P as a pseudo P subgroup and such that the fusion system of the block is the fusion system of that finite group H. So we do not have an answer to this question. It's one of those big unsolved mysteries. New blocks actually give new fusion systems. And so now with these two ways of defining categories on key clues in mind, so Puig wrote down a set of axioms. It has evolved a little bit over time, but that set of axioms captures the properties of fusion systems of blocks and of groups in an abstract fashion, and leaves very little room for fusion systems that do not come from these two sources. I'll say something about that in a moment. So I mean, I put 1992 there because Puig talks about this in 92 and Harris, well, he starts out as a finite P, and so then defines well, what we now call saturated fusion system. Puig did have a very different terminology at the time. Objects are obviously the subgroups of that finite P group, and morphisms. And there we have to work a little bit to get to the list of axioms that define morphisms. So first of all, morphisms have to be sets of injective group homomorphisms. That's because in fusion systems of groups, that's how it works. And you also want to make sure that this inclusion and the second last line, that all homomorphisms that come from conjugation within the defect group or within the group P are actually contained in that set of injective group homomorphisms. So you want that. And then these sets of group homomorphisms have to satisfy a couple of axioms. And in order to state those axioms, I mean, topology. So the funny thing is, when you take the normalizer in a group G of a P subgroup Q, and you intersect that with a pseudo subgroup of G, you may not get a pseudo P subgroup with the normalizer. You may get something small. But elementary group theory will tell you that after conjugation, you can always achieve it. And this is what this definition captures. So a subgroup Q of P is called fully F-normalized if its normalizer in P of Q is as big as it possibly can amongst all members of its F isomorphism class. So you may have all these subgroups of P that are isomorphic in the fusion system, but the normalizers in P may be different. And you pick one which has a normalizer of maximum possible order, and those that do have this property will be called fully normalized. And the trickiest bit is the definition of this group. So you have a morphism from Q to P in F. And you want to look at those elements in the normalizer in P of Q, which consists of those elements Y, for which there exists an element Z, which normalizes the image phi of Q, such that these conjugations can be defined, such that first conjugation by Y and applying phi is the same as first applying phi and then conjugation by Z for all U and Q. So this is a subgroup of the normalizer of Q in P. It contains Q because it contains Q simply because you can then apply phi. If Y does belong to Q, you just apply your Z's just by Y. It also contains the centralizer P of Q. That's because the centralizer doesn't do anything, so you can take second as well. So with these two notions, they're really, you know, at the heart of this this definition. This is what I just said. We can state those two additional axioms that the morphism sets have to satisfy. Actually, the first one I could have stated before is just a pseudo axiom. It just says that if you look at the automorphisms that come from conjugation within P on P itself, these are just automorphisms of P. They are a subgroup of the automorphisms in F of P just because I make this a requirement that everything that comes from conjugation within P belongs to the fusion system. And I'm going to require that this is a pseudo-primitive group of that automorphism. The second condition is the really tricky one. It's an extension axiom. For every morphism in the fusion system F, such that the image is fully normalized. You know what that meant? That meant that the normalization P of that thing is maximum possible. You can extend this phi to a morphism to this figure called N phi. And as I said, this doesn't make sense because Q is contained in some phi. And now it's in exercise, just using pseudo theorem in a smart way, that the fusion system of finite group G on what its pseudo pizza group, this is always a saturated fusion system in the sense of the spatial dimension. You might wonder, okay, so pseudo axiom, yeah, it's easy to believe because we're talking about the normalizer modular P times the centralizer, so yeah, that's a P prime group, so definitely the pseudo axiom is going to work. What about the extension axiom? So the extension axiom, again, justifies a tricky way that you have a pseudo theorem, not just for the group G, but also centralizes the normalized of G. And so if you want to really get a feeling for fusion systems in this abstract definition, do run once through this proof that the fusion system of a finite group, etc. And it's easy. Yeah, you even without, with what I have told you, just sit down in an hour. As I said, the proof is elementary group theory. Pseudo axiom is straightforward because this automorphism group modular in automorphism is isomorphic to this prime group quotient. And now, of course, the reason why we introduce saturated fusion systems is that fusion systems of blocks can be shown to be also saturated. Now, that's not something that you do. I'm sitting down for an hour without any further block theory. So this is actually a painful proof. So you have to really work on this one. So historically, it's interesting. So Brower was kind of aware of the fact that there must be something like that for blocks because he already had actually the notion of centrics in the defect group, and he didn't write down these categories. So as later after going into this, and then that led to Puig's definition of the abstract fusion systems. So I should make a mention about what happens if K is not algebraically closed. It's quite interesting what happens because you can still write down everything, all the definitions that make a perfect sense. It's interesting that the resulting category that you get is almost a saturated fusion system. The only axiom that goes out of the window is a pseudo axiom. Extension axiom is still in the picture. And I did mention the word centric in a second ago, and I'll just say what centric subgroups are, because they are one of the key ingredients for understanding the structure of the abstract fusion system. What we call centric is those subgroups Q of P, on which we have a saturated fusion system, which has the property that their centralizer in P is actually their center, so they're self-centralized. but we make this a requirement not only for the group Q itself, we make that a requirement for all the groups isomorphic to Q in the fusion system. And we have to do that because the property of being self-centralizing P is not an invariant of the F isomorphism class. We have to require this for all of them. So it's a typical fuzzy thing that one needs to deal with. So here are a few properties. Well, obviously, P itself is eccentric, so there's nothing to say because centralizing P to central P. Well, the eccentrics are upwardly closed in the sense that if you start out with you have a morphism in your fusion system, and the group that you start out with is eccentric, well, then the bigger group R, the target group, is also eccentric. It's a nice and easy group theory exercise. And centric in fusion systems of finite groups means something very simple. It just means that the central CG of P in G has the center as a pseudo P sub group. And in that case, the centralizer decomposes, this is the classic theorem, as direct product with center Q and a P prime subgroup C prime Q. So again, the C prime Q is then the open parameters group is the largest normal and we denote by F with a little c up there, this full subcategory of all F centric subgroups in P. And I think I'll just have time for one more slide here. I want to just mention upright fusion theory. So one of the things one needs tools for is to decide when you have two fusion systems, well, when do you know that these are equal? And upright fusion system theory does tell you something there. Namely, it says, well, actually, you know it if you know the automorphism groups of the centrics in the fusion system. Then, okay, so this is the informal way of writing down upright fusion theory. I have to be a bit more precise here. What do I mean exactly by that? Well, what it means is that every morphism in F is a composition of morphisms which are the restrictions of automorphisms of centrics. So every morphism can be written as a composition of morphisms from Q to Q prime, for which there exists an F centric which contains both of these, Q and Q prime, and an automorphism of that centric, which restricts to the morphism phi on restriction of Q. And this is not the most general version for the experts. Obviously, we can replace eccentric by a small set of what we call central subgroups of P. And in that version, it started out by Alvin, which I mentioned also Alvin bullshit for the more sophisticated version with the centrals, and then extended to our fusion systems by Puig. I do want to mention here the theory of Burnside, which works for arbitrary fusion systems, which says that if you have an arbitrary fusion system on a finite or dual P group, then you don't get anything new. You only get fusion systems of finite groups of that same simple shape, semi-direct over P with something that P prime actually on top of it, and E is just, in this case, the automorphism written F of P. And I think it's a good time to have a break here, and I could move on. So, thank you.
So we mentioned in the conjecture that basically for like the fusion systems for blocks, that the question is whether to use like new categories, like find that. And the conjecture said that basically like every fusion system given by a block is equal to the fusion system given by groups. Is there some version, maybe proven in some cases where instead of equality, we have an equivalence of categories or something more lax than equality?
Yeah, so, I don't actually know whether the equivalence of categories is a significantly different notion for quality of fusion systems. So, or when we say that two fusion systems are isomorphic, then what I really mean by that is there's an isomorphism between the two Pisa groups, which induces and the relevant equalities of morphisms. That is slightly more stringent than just asking for an equivalence of categories. So I'm not sure actually what the answer to that is.
Thank you.
Question?
Yeah, you mentioned that if K is not algebraic closed, then the fusion system for the block might not be saturated. Is there any interest in this type of fusion system? Is there any points studying this?
So, so there's a paper by Puig and Yilmaz, which investigates what happens for blocks if you use blocks over finite fields. And what they find is that the fusion systems in that case are not saturated, but they are basically a saturated fusion systems extended by a cyclic automorphism on the top P group. And so I'm not sure whether anybody, whether there's a very well developed theory of fusion systems of that type in general. But we definitely do need to look at these in block theory, because lots of the conjectures that we have, we would like to ideally be able to write them down over FP with Brandfield, and because then they would extend to all bigger fields almost automatically. So this is a dream. So we do need to look at this. Yeah, but so yeah, the theory needs to be already developed. Okay.
Further questions?
Well, if not, let's thank Markus again.